Welcome to the Explainer. Today we're diving into a seriously fascinating new astrophysical study by researchers Shauna Selman and Eric Corpela. We are looking at the actual real-world physics of extraterrestrial mega-engineering. Taking those wild concepts that usually just live purely in sci-fi and running them through some rigorous mathematical astrophysics. Let's get right into it. So picture this. Imagine a scenario where an incredibly advanced alien civilization has totally outgrown its planetary boundaries. What if they intentionally wanted to alter their planet's climate? Or what if they just wanted to light up those long, freezing nights on the dark side of their world? To pull that off, they wouldn't just be building bigger ground-based spotlights. No, they'd be constructing massive orbital hardware. And that right there brings us to a really crucial concept for astronomers today, the technosignature. For a long time, the search for life focused heavily on just listening for radio waves, right? But a technosignature is a physical, measurable property. We're literally looking for the cosmic footprints of alien mega-engineering.
Section 1. Giant mirrors around exoplanets. The mega-engineering blueprint.
Okay, the sheer scale we're talking about here is just fascinating. The authors analyzed this hypothetical fleet of orbital mirrors, and they are massive, 1 kilometer by 1 kilometer in size. Just think about that surface area for a second, a full square kilometer. But here's the crazy part. According to their models, these giant structures weigh a shockingly lightweight 1,000 kilograms. To put that into perspective, that's roughly the weight of a standard compact car, but stretched out over an entire square kilometer of space. It's wild. So because of those extreme dimensions, you kind of have to imagine a super delicate solar sail caught in a literal hurricane of starlight. That's the reality for these hypothetical mirrors. They have to be extremely large to catch as much starlight as possible, but because they are so lightweight, they're incredibly delicate. And honestly, that exact physical makeup creates a massive astronomical problem. Which brings us to Section 2, the radiation pressure problem, the physics clash. The core issue here is this intense cosmic tug-of-war. On one side, you've got gravitational acceleration from the exoplanet, right? It's desperately trying to hold the mirror in a stable orbit, pulling it tight toward the planet's center. But on the other side, pushing back, we have radiation pressure, or RP. See, light actually carries momentum. So when intense starlight hits a massive, super lightweight mirror, it physically pushes against it. And because the mirror is so unbelievably light, that push is substantial. As the authors point out in their paper, this radiation pressure is so significant that it becomes a legitimate existential threat to the megastructure. If the balance isn't absolutely perfect, the radiation pressure could completely destabilize these mirrors. Best case, they lose their orbital velocity and go crashing down into the alien planet. Worst case, they act way too much like a solar sail, get blown entirely off course, and just get flung out into deep, empty space. Section 3. Simulating orbital survival, running the numbers. To actually figure out if these things could survive, Salmon and Corpela had to accurately model all these exact physical forces. To do this, they used a highly specialized simulation package based on the RBON N-body simulator. Now, this is a seriously powerful computational tool that astrophysicists use to track how multiple bodies in space interact gravitationally over time. And for this study, they specifically tweaked it to incorporate the intense effects of radiation pressure from starlight. The parameters they plugged into the simulator really showed just how rigorous the scope of this study is. They didn't just test one simple, perfect scenario. Nope, they tested the mirrors in the habitable zones of 8 entirely different types of main sequence stars. They varied the starting distance, putting mirrors in initial circular orbits ranging anywhere from 2 to 10 planet radii away. They even tested 4 different initial orbit orientations just to see how the starting angle mattered. And fascinatingly, they toggled the radiation pressure itself. They tested what happens if the starlight hits the mirror constantly versus what happens if the mirrors are angled to only catch the light during the orbital night, specifically when they're trying to illuminate the dark side of the planet. And for every single one of those incredibly complex simulation runs, the team meticulously tracked 4 specific data points at every single moment in time. They tracked the absolute survival time, basically how long until it either crashes or escapes. They plotted the specific trajectory it took. They measured its exact distance from the planet's center. And finally, they recorded the relative velocity, which is the speed of the mirror compared to its host planet.
So by crunching those 4 data points, they generated 2 major comparative steps. First, they calculated the exact mathematical ratio between the force of the radiation pressure and the force of gravitational acceleration. Then second, they calculated the ratio of the host planet's orbit period compared to the mirror's orbit period. By aligning these specific ratios, they hit step 3, uncovering the precise, overarching trends. They essentially built a complete mathematical map that predicts exactly when, where, and under what star types an alien mirror would stay perfectly stable, and when it would just be totally destroyed.
Which leads us to Section 4, the hunt for technosignatures. Why this matters. Ultimately, this research provides a literal blueprint for human astronomers. Look, telescope time is incredibly expensive, and as we all know, the universe is impossibly vast. We simply can't look everywhere. But if Salmon and Corpella's math proves that a giant, lightweight mirror just literally cannot survive in a specific orbit around a certain type of star because of that radiation pressure, well, then we know we can safely skip scanning that area. It tells us exactly where not to look, which by process of elimination tells us exactly where we should be looking. It makes our active search for these technosignatures drastically more targeted and way more efficient. Studies exactly like this one remind us that finding extraterrestrial intelligence isn't just about hoping to intercept some random hello on a radio dial. It's really about understanding the raw physics of advanced engineering well enough to actually know where to spot its shadow. As we continue to refine our simulated models, gazing into the habitable zones of distant stars, armed with this brand new mathematical blueprint, we really have to ask ourselves, if these megastructures are actually out there, are we finally ready to see what's been hiding in the light?